want to analyze important ideas. And before BMO round 1 2022, 2023, I released a video preparation. In that video, I told you a lot of important things, and I use many of them in BMO round 1 of this year. Also, I will use again same ideas for solving 1 and 2. And you should learn general ideas that are useful for BMO round 2, BMO round 1, AMC, AME, CSAT, SAT, the exams for applying top universities. So let's see how we can solve this problem. Let's start with problem number 1. It says let ABC be a triangle with an obtuse angle A and in center I. So let me draw the figure. Okay, it is a figure. A obtuse angle A, in center I. In center means intersections of angle, internal angle bisector, and it is also center of in circle, the circle that is tangent to all 3 sides. Circle ABI and ACI, ABI, ACI intersect BC at again an X and Y. And let me tell you something. BMO and BMO is for UK, AMC, USA, AMO, all these things are for USA. These 2 exams are most prestigious exams in Olympiad in the world, in national level. Okay, so it says circles ABI and ACI intersect BC again at X and Y. Okay, look, this circle, X and Y. The lines AX and BI, AX, BI meet at P, this point. And the lines AY and CI, AY, CI meet at Q. Prove that BCQP is cyclic. BCQP. Okay. When we want to prove that a circle is cyclic, a quadrilateral is cyclic, there are 4 rules. 2 of them related to angles, 2 of them related to lengths. For example, if ABCD is cyclic, the first rule is that you say, okay, ABCD is cyclic if and only if ABCD is cyclic if and only if A plus C is 180. One rule is this. The other rule, you can say 2. Let me copy this one. If the first 2 rules related to angles, this one says that if we connect this, A1 equal to B1 if and only if ABCD is cyclic. Means the angles that see the same side are equal. It was second rule. Third rule, ABCD is cyclic if we draw the diagonals. It is related to lengths. If we consider intersection P, then we can say ABCD is cyclic if and only if AP times PC equal to BP times PD. And the last one, fourth rule. Let's draw. You should extend the 2 sides here. And look, each of them has proof, and the proofs are basic. You can use without proof because they are so much famous in exams that needs full solution. So here again, ABCD is cyclic if and only if PA times PD equal to PB times PC. So we should select from these 4 things which of them useful here. If we want to work with angles, PQ, look, we should prove BCQP cyclic. So if we, for example, draw this angle is good. It's B half because BI is internal angle bisector. But here it's a little hard to work with. And also we will see angles are not so much good. And if you want to use third rule about lengths, we should consider the diagonal. Again, we will say, okay, we should draw 2 new lines. So let's see what about fourth condition. We should extend. And here you will see that I is intersection of extensions of CQ and BP. So because we don't need to draw any new line, let's check this one first. Okay, so we prefer not to draw too many lines and consider angles that we should draw new lines. So here I say PQCB is cyclic by fourth rule that I told you now, if and only if IP times IQ equal to IP times IB, equal to IQ times IC. IB and IC are better than IP IQ because IB, look, it is B, we know it is vertex of the triangle ABC and I is in center. So we should focus on IP IQ. Let's consider something. We know these two angles are equal, both of them are B half. So, and it is a cyclic quadrilateral, so these two arcs also are equal because they are opposite to these two angles. Now let's draw lines. This line, this line, this line. Then we can say, okay, this is for some 1 point angle. It is equal to this. Why? Because it sees this one. See the same arc. And they are inscribed angle, half of the arc they see. Also, these two angles are equal. So we can say these two angles also are equal like this. Okay. So because these two angles are equal, IAP, let me call this one, for example, I want to say IA equal to IX. Look, angle IAX equal to angle IXA. So we can say the IAX is isosceles triangle, IA equal to IX. These two lengths. Also, we can say, because it is C, these two angles are equal to points, because CI is internal angle bisector, this is equal to this one equal to this one, so we conclude that these two angles also are equal, and we can say because angle IAY equal to angle IYA, so we can conclude IA equal to IY. Now, because IA is same, we conclude that IA equal IX equal IY. Okay? Now we want to see how we can relate it to IP. Now I want to, for finding IP, I want to use a sine rule in this triangle. Okay? A sine rule for preparation of BMO1 and also AMC. I released video before that. I told you sine rule, cosine law, all these things, and I explained are important in many math exams like here. So we should focus, we should use a little angle chasing. We know 1 point is B half. So this angle is also B half. And we know this angle is A half because AI is internal angle bisector. This angle is B half because it is 1 point, it is this. So we can say this angle is A half minus B half. Okay, if you have any question, feel free to send message to my WhatsApp number in the description and comments. So look here, A half, B half. Why it is B half? Because it is equal to this. They see the same arc. 1 point is B half. The whole part, because AI is internal angle bisector, is A half, so it is A half minus B half. And we know this one is also B half. And now we can say this angle is what? This angle is exterior angle of this triangle. Okay, so it is sum of non-adjacent angles. A half minus B half plus B half. So it will be A half. Okay. Now let's use sine law in triangle PXI. Sine law in triangle PXI. So we can say IX over sine. Look, we should consider sine this angle. It is what? Sine 180 minus A over 2. Equal to PI. PI over sine B over 2. PI over sine B over 2. And let me tell you, here we should prove this because we want to prove PQCB cyclic. The other things are assumptions and the conclusions we've reached. Now, let's focus on this. We know that sine 180 minus some alpha, for example, equal to sine alpha. So we can say ix over sine a over 2 equal to pi over sine b over 2. So we can say pi equal to sine b over 2 over sine a over 2 times ix. Now, pi is for what? For part B from vertex B we see. IQ is what you see from vertex C. So all things are same, only here you should see from C. And similarly, we can say that IQ equal to sine C over 2, because B changes to C, A same, A over 2, times, instead of IX, because IX was related, you should say IY, and we know all of them are equal, IY. Now, we want to find, for example, IP, IQ, IP over IQ. Let's divide, okay? Divide these two terms, so PI over IQ, let's see, it is equal to what? Sine B over 2 over sine C over 2, sine A over 2 will be cancelled, times IX over IY. And we've proved IX equal to IY, we can call it a star. I star, you can cancel that, and you can say it is equal to sine B over 2 over sine C over 2. Now, if you consider triangle BIC, okay, triangle BIC, we can say IB over sine C over 2 equal to IC over sine B over 2. Okay, so we can conclude, let me write it here, IB in triangle BIC sine law, IB over sine C over 2 equal to IC over sine B over 2. And because here we want what? We want sine B over 2 over sine C over 2. So we conclude sine B over 2 over sine C over 2 equal to IC over IB. So we can write here it is equal to IC over IB. Now, if we cross multiply, we consider this term, we conclude Pi or IP times IB equal to IQ times IC. It was exactly the thing that we wanted. IP, IB, IQ, IC. IP, IB, IQ, IC. We proved this. So by fourth rule, we proved PQCP is cyclic. Okay. So here, look, we only needed fourth rule, but I told you all four rules that are useful in some problems. Only first one useful, sometimes some of them useful. You need to apply more than one of them. It was related, and it is also useful in AMC, AME, USAMO, IMO, cyclic quadrilaterals are so much important, and how to apply. Also in BMO1, in many years it's useful. So if you want to learn other important formulas, and as I said before, there are around 40-50 formulas in geometry, also in other topics, combinatorics, number theory, algebra, you should memorize them. If you want to learn them, feel free to send message to my WhatsApp number in the description and comments. Now we can jump into problem number 2. Problem number 2, it says for an integer n greater than 1. Before solving this, before BMO preparation, I told you, and also before AMC, before BMO1, I released the video. Exactly, I told you the idea here. For these types of problem, you should consider small examples and find the idea and generalize that idea. In many cases, you should use also induction. So let's read. It says, and again, we solved this problem with the same idea also previous year. We had problem that was in all years. We have problems that we can use this idea. So if you want to learn how to apply this important idea, considering a small example, how to find not only pattern, you should find idea behind the problem and then generalize that. How you find the idea behind the problem? By considering a small example. So it's an important technique. So, and strategy. So let's read. For an integer n greater than 1, the numbers 1, 2, 3 to n are written in order on a blackboard. The following moves are possible. Take three adjacent numbers x, y, and z, whose sum is a multiple of 3, and replace them with y, z, x. The next rule. Take two adjacent numbers x, y, whose difference is a multiple of 3, and replace them with y and x. For example, we could take, so let's see, it says 1, 2, 3 to this one, but first rule. Let's see, 2, 3, 4. The sum of 2, 3, 4, because it says the sum should be multiple of 3. For example, look, 1, 2, 3 also, the sum is 6, 2, 3, 4 is 5 plus 4, 9. So you can apply first rule, then 4 will, let's see, sorry, for 1, 2, 3 it applies. So, for this one, 3, I like this one, x, y, z, x goes to the last one. First one goes to the last one, 2, 3, 1. And then second rule, it says we apply for 1, 4, because their difference is multiple of 3, 4 minus 1, 3. You switch 4 and 1. And then it says find all n such that the initial list, which is 1, 2 to n, can be transformed into n, 1, 2 to n minus 1 after finite number of moves. Okay, because it says n greater than 1, let's check n2. 1, 2, you should change it to 2, 1. Is it possible? No, because we have only 2 elements. So n2 is not possible, and their difference is not multiple of 3. Let's check n3. We want to see, is it possible to move 1, 2, 3 to this one? 3, 2, 1. So 1, 2, 3, if we apply first rule, then you can say what? Let me tell you something. It says you can reach from x, y, z to x, y, z. If you apply this again, look, first one goes to last part. It goes to last part, it will be z, x, y. If you apply this again, you will reach again x, y, z. So as you can see, it seems that, for example, x, y, z are lie on a circle. Okay, so as you can see, let me correct this one because it is 3, 1, 2. So for better simplification, that is useful in, also in SUMAC, this idea was useful, Stanford summer camp. You can say, for example, you can rotate x, y, z clockwise in each step 1 unit. And let me tell you, if you rotate it twice clockwise, it is equivalent to once counterclockwise. Okay, because when you rotate it 3 times, it will be same. So 2 clockwise is equivalent to 1 counterclockwise. So it means that for working with second rule, you can consider any 3 terms. You can rotate it circular, clockwise or counterclockwise. Now, for example, here you say, okay, we will rotate 3 here, 1, 2. So with one action, you can reach this. Now, so n3 was okay. Let's check another numbers. For example, n4. 1, 2, 3, 4. We want to reach 4, 1, 2, 3. So, because we want to move 4 from last one to first one, we consider this part first. 4 plus 3, 7 plus 2, 9. So you can rotate and we can reach. So here we want to reach how? We want to see how we can reach. So you can say 1, 4. After 4 is 2, then 3. You rotate. Now for 1, the difference of, so it was second rule. From first rule, you can use this, you can switch 1 and 4 because their difference is multiple of 3 is 3. So it will be 4, 1, 2, 3. So with first rule, we can reach this. So n4 was also okay. Now, let's check next one. n5. We have 1, 2, 3, 4, 5. We want to see, can we reach to 5, 1, 2, 3, 4. Okay. By first rule, if I want to 5 plus 4, 9 plus 3, 12. For example, if we use this, you can say, okay, I move it 5 here, then 3, then 4. Then 5, 2, their difference. 5 plus 2 plus 1 is not multiple 3 if we apply it. So second rule. If we apply first rule again, you can switch 5 and 2. It will be 1, 5, 2, 3, 4. So now we can't do this. But here you can't say 5 is not possible because maybe we couldn't, for example, do this. Someone can do something better and reach. So we don't know. And 5, we couldn't find a way. So and we guess. Look, I draw with dotted line because we guess that N5 is not possible. Because if you check many cases, you will see it's not possible, but we've not proved yet. Okay, we are just working on the solution and we don't write these things on an answer sheet. All things are for ourselves. Then we guess which numbers are okay, then we try to prove. After that, we write the solution on answer sheet. So let's check N6. If we work on N6, we want to reach from 1, 2, 3, 4, 5, 6 to 6, 1, 2, 3, 4, 5. Okay, so for 6, sum of 6 plus 5, 11 plus 4, 15. We apply second rule. It will be 1, 2, 3, and 6, 4, 5. Now, if we use first rule, let me see second rule, third rule. What second rule? Second rule, only 2 elements, so I think I should correct. Second rule, 1, 4, 3. Okay, so this was first rule, this was second rule. Okay. And this one, 1, 2, 3, second rule, no. First rule, second rule. And here, by first rule, we can reach this. Now, by second rule, we switch 3 and 6 because their difference is 3 and multiple of 3. 1, 2, 6, 3, 4, 5. Then here, 1, 2 plus 2 plus 6 multiple 3. If we apply first rule, we can rotate. Look, we see how many times we need. We rotate such that 6 comes here, 1 comes here, 2 comes here, 3, 4, 5. So we could, for N6, it was possible also. Let's check N7. Here, look, we guess all things are related to 3. 3k, 3k plus 1 possible, 3k plus 2 is not possible. So, for 5, let's see 7 is possible or not. So, we want to reach from 1, 2, 3, 4, 5, 6, 7, 2, 7, 1. Okay, so 7, 1, we want to see is it possible to reach 7, 1, 2, 3, 4, 5, 6. Again, we focus on 7 to take it to first place. So if we consider this one, some of them multiple of 3, and we apply first rule, it will be 1, 2, 3, 4, 7, 5, 6. Now we apply second rule for this part. It will be 1, 2, 3, 7, 4, 5, 6. Then 7, 3, 10, 12. We apply first rule here. It will be 1, 7, 2, 3, 4, 5, 6. And then we apply second rule for this part. And we will reach the arrangement we wanted. Okay, so it was possible. Now we guess. We guess that n equal to 3k. Okay, 3k plus 1. Okay, 3k plus 2 is not okay. Now, for 3k plus 1, it is our claim. We want to prove this. So, we should consider 3 cases. For 3k, why we can. For 3k plus 1, again, why we can. And why for 3k plus 2, no one can reach the destination, the last permutation the problem wants. So, we have 3 cases. In first case, let's consider n equal to 3k and let's solve. We want to reach from 1, 2, 3 to, for example, 3k minus 4, 3k minus 3, 3k minus 2, 3k minus 1, 3k. How we can reach from this to this one, that 3k, 1, 2, 3. We want to take 3k to last part. 3k, for example, minus 2, 3k minus 1. Okay. So let's start. We can say we have 1, 2, 3. Let's consider 4, for example. 3k minus 4, 3k minus 3, 3k minus 2, 3k minus 1, 3k. In first level, you see their sum is multiple of 3 because it's 9k minus 3. So we can move 3k here, 3k minus 2 here, 3k minus 1 here, and then 3. So by which rule? By first rule. And 3k minus 3, 3k minus 4, and 1, 2, 3, 4. Okay. Now from this part, we can use second rule to apply this one. So it will be 1, 2, 3, 4, 2, 3k minus 4, 3k, 3k minus 3, 3k minus 2, 3k minus 1. Now let me tell you something. Here you can do again this thing 3k, 3 ones and 1 1 like this, or we can use induction. You can say here we have 1, 2, 3k minus 4, for example, like this one is similar to 3k minus 3 because both of them are multiple of 3. So we can reach this by induction to 3k, 1, 2, 3, 4, 3k minus 4, and rest. So we've used what here? We've used 3k minus 3 and reached 3k. Okay, and so in base case, for example, you can say, okay, you checked 2, it was not possible, 3, and because we want to only prove the things we want for this case, for case 1, you need base case 3. Okay, and so 3k minus 4 and the rest, or 3k minus 3, 3k minus 2, 3k minus 1. So we prove first case by induction. Now let's consider second case, which n equal to 3k plus 1. Again, we write all things we have. 1, 2, 3, 4, 3k minus, for example, 5, 3k minus 5, 3k minus 4, 3k minus 3, 3k minus 2, 3k minus 1, 3k, 3k plus. And then, if we use first rule here, their sum is multiple of 3. It will be 1, 2, 3, 4, 3k minus 5, 3k minus 4, 3k minus 3, 3k minus 2, and here 3k plus 1, 3k minus 1, 3k. It was now we use second rule to switch these two things. It will be 1, 2, 3, 4 to 3k minus 1, 3k minus 4, 3k minus 3, 3k plus 1, 3k minus 2, 3k minus 1, 3k. And look here, if we consider this one, you can use induction. And we can say again 3k minus 1, the next one is 3k minus 2. And both of them, 3k minus 2 and 3k plus 1, both of them, the remainder when divided by 3 is 1. So they will be same. Because the two rules, mod 3 is important, divisibility by 3. So because these two numbers are same, we can use the same thing, we can use induction. And this case 1 and 2 were same. We could also say 1 to n and use the same thing from n minus 3 to n. So then we can prove part 1 and 2 with one step. So we can do 3k plus 1, 1, 2, 3, 4, 3k minus 5, 3k minus 4, 3k minus 3, and then also we have these things, 3k minus 2, 3k minus 1, and 3k. Okay, we could reach this one, and we proved that if n 3k or 3k plus 1 is okay. Now we should prove that 3k plus 2 is not possible. For 3k plus 2 that is not possible, we should use invariant. We should define a function. And look, the most important thing is how to find a good function. So n equal to 3k plus 2, because look, when we want to change, for example, two numbers, let me tell you, for example, 5. We want to reach from 1, 2, 3, 4, 5 to what number? To 5, 1, 2, 3, 4. If we consider mod 3, the first arrangement is 1, 2, 0, 1, 2, and we want to reach 2, 1, 2, 0, 1. Okay? We want to say it is possible. It is impossible. So the first rule was what you consider, for example, 3 elements. We want to say also it is not possible to reach from this arrangement to this arrangement. Also for mod 3, if you consider it is not possible, so we can say the main part also is not possible. So in first rule we said if x, y, z, the sum of them multiple of 3. Sum of them, x plus y plus z, is multiple of 3. So what are the cases? One case 0, 0, 0, 1, 1, 1, 2, 2, 2, 0, 1, 2. Now we will see that 0, 0, 0, if you change them again, it will be 0, 0, 0. So it has no effect, only we should consider 0, 1, 2. Okay? So for example, if you have 0, 1, 2, you can rotate it. You can go to 2, 1, 0, or you can go to, you can rotate it again, 0. Sorry. Let me correct this. After 2 is 0. 2, 0, 1. And if we switch again, it will be 1, 2, 0. And if we start with 0, it will be. So we can change it to these two things. And for second rule, it says if two things are same when divided by 3, their difference multiple of 3. So we can say x, it is x, because we only consider mod 3. You change it to x, x. So it has no effect on our arrangement when we consider mod 3. So our only movements are this. We can move, for example, 0, 1, 2 to 1, 2, 0 or 2, 0, 1. Now, the most important thing, what is our function? I want to define a function that, for example, f here is something, f here is something, but under this condition, this movement, this action, f won't change. F is stable. It is invariant. This is so much important lesson. Many problems of SUMAC, Stanford Mathematics Camp, Stanford University Mathematics Camp, could be solved 2023, 2022, could be solved by invariant, but you should define function. It's not so much easy, but if you solve some problems, you will get what functions are good. So here I define, let me explain for you. I define one function. For example, suppose the first element is 1, it is a1, it is 2, it is a2, it is 3, it is a3, and so on. For example, it is n, it is an. We define f as 1 times a1, the position, times the number inside. 2a2, 3a3, up to nan. Okay, we define f as this. Now, let's see for this example, then we generalize for general n3k plus 2. Here, and we consider f mod 3. This is the first place, the second place, third place you can say it is 0. Fourth place, again you can say it is 1. Fifth place, it is 2. So f here, let's calculate, is 1 times 1. We consider mod 3 all things. 1 times 1, 2 times 2, 4, it is 1. So it will be 1 plus 1 plus 1 plus 1, which is 4 here, which is 1. Okay, we consider mod 3 all things. Here, you say here, it is 1, first place, second place, third place, again, fourth place, second place. it will be 2, 2, 2. So it will be 2 plus 2 plus 2 again, which is 6, which is 0. So f1, 0. Now, I want to prove that f won't change under these actions. So let's see. For example, suppose that it is, for example, it is I plus 1, it is I plus 2. And we have x, y, z, and we know x plus y plus z is multiple of 3. Okay? So let's see if f won't change mod 3, it will be good. So suppose, for example, you rotate. You say, okay, z comes here. If we consider the first action of 2, y, z, x. Okay. So x goes to the end. So we can say x, and then we consider y, z. But the previous part was also okay. Rotation it is. I explained the beginning of the video. So let's see under this action what's the effect on f. So the first part is xi plus I plus 1y plus I plus 2z. Now let me tell you something. Because x plus y equal plus z is 0, so we can say z equal to negative x minus y mod 3. So you can replace by that. So if you replace with that, it will be mod 3 xi plus I plus 1y plus I plus 2. Instead of z, we replace it with negative x negative y. Okay? So it will be ix plus iy plus y minus ix minus iy minus 2x minus 2y. Ix, iy, iy. So it is congruent to plus y minus 2x. It is the first part. Now let's apply second part. This iy plus I plus 1z plus I plus 2 times x. And it is congruent to iy plus I plus 1 z, which is negative x minus y, plus I plus 2x. It will be iy minus ix minus iy minus x minus y plus ix plus 2x. Ix negative ix will be cancelled, negative iy will be cancelled. 2x minus x is x, and it is x minus y. Okay, now I want to prove that these two things are congruent mod 0, mod 3. So this part and this part. So if I want to check this, I can say, okay, minus y minus 2x is congruent to x minus y is equivalent that you add 2x plus y to both sides. So left side will be 0, right side will be 3x plus y will be cancelled. So 3x is congruent to 0, mod 3, it's okay. So we will see under this action when we do this, it has no effect on f. So here f was 1, f here is 0, so it is impossible to reach this. Now we want to do this for other 3k plus 2. So let's prove in general. Suppose n is 3k plus 2. The first configuration is, you say, in first place, you have 1. In second place, you have 2. In third place, like this. Let me show you. In third place, you have 0. Third place, you can say 0, 0. In fourth place, which is 1, you have 1. In fifth place, you have 2. It's 2. In sixth place, it's 0, 0. So for 3k plus 2, it is 0, 0, 1, 1, and 2, 2. Okay. Now it wants to reach 3k plus 2 here. So 3k plus 2 will be here, and then 1 here, then 2 here, then 3 here, 0, then 1, 2, 0, and 3k plus 2. 3k plus 1, the last one will be 1, 0, 2, 1, 0. And here it will be 1, 2, 0, 1, 2, 0, 1, and the last one, if we want to consider the cases, it's 3k plus 2 is 2, 1, 0, 2, 1. Okay. Now f here is what? 1 times 1, 2 times 2, all of them. 1 squared plus 2 squared plus 1 squared again plus 2 squared up to last one. So if you consider mod 3, all of them will be 1. And we have how many? 3k plus 2 terms. How many 0 are there? Minus k. It will be 2k plus 2. Mod 3, it will be, yes, 2k plus. Let's consider something. Now, look, a small example. Here you write this in your answer sheet, but you have these things you can check. For example, for this part, it says f equal to 1. Here it was 5, and 3k plus 2 is 3, 1 plus 2. So 2k plus 2 to 1 plus 2 will be 2 plus 2, 4 is 1. So here we've reached 2k plus 2. Now we want to consider f for this part. It is 2, again plus 2, then you have 2 zeros, okay? Then you reach 2, then you reach 0, then you reach 0, okay? And so we will see here, we have 2, 0, 0. Again, we have 2, 0, 0. So from here, we have something like this. Again, 2, 0, 0. Plus the last part, 2. So how many 2's are there? 3k. We have 3k plus 2 numbers. You subtract by 2, 3k over 3 plus 2 other 2's here. So it will be 2 times k plus 2, which is 2k plus 4. Okay. So if you consider mod f won't change mod 3 under the actions the problem wants. So if we can reach by a contradiction 2k plus 2 should be congruent to 2k plus 4. Then we conclude 2 is congruent to 4. If we subtract by 2, 0 is congruent to 2 mod 3, but it's not correct. So we consider that if we reach, then we've reached contradiction. The most important part of this problem was defining this function. Maybe you say, okay, from what place I understood this function is good? Look, there are some, for example, sum of production, sum of squares, sum of variables, product of variables. There are some general things like these. In many problems, they are useful. And look, it was not the first function I've checked and was correct. I checked different functions. Many of them were wrong. And then I reached this function that works. Okay, so if you want to learn these things and the ideas, as I told you, important ideas in combinatorics, 40, 50 important formulas and ideas you should learn in geometry, combinatorics, number theory, and algebra, useful in BMO, IMO, AMC, AME, USAMO, and other national Olympiads, and also International Olympiads, IMO. If you want to learn them, feel free to send message to my WhatsApp number in the description and comments. Okay, let's solve problem number 3 of BMO round 2 2023, British Mathematical Olympiad. Okay, in this problem, again, I want to use the idea I used in problem number 2, same idea. At first, pause the video and try by yourself. I want to use again and again small examples and find the idea and generalize it. And as I told you before, also in BMO preparation, I told you this idea is so much useful. I can say in all years of BMO 1 and 2, we can use this idea. And for example, in this year, 2 out of 4 means half of problems can be solved with this idea. So let's read the problem. It says for any integer, for an integer n greater than or equal 3, we say that a equal to a1, a2 to an is an n-list if every ak is an integer in the range 1 to n. For each k from 1 to n minus 1, let mk be the minimal possible non-zero value of this term a1 to ak plus 1 over ak plus 1 minus a1 to ak over ak absolute value of this term across all n lists. We say that an n list A is ideal if this absolute value equal to mk for each k1 to n minus 1, a1 to ak plus 1 over ak plus 1 minus a1 to ak over ak absolute value of that. Find the number of ideal n lists. Again, I want to use a small example, suppose N3 and on. Understanding this problem is hard. We cannot understand completely when we read for the first time. And if you read again and again, maybe you can't understand. But if you work on a small example, you can also understand problem means what. So let's check N3. It says for K1 to 3 minus 1, which is 2. So if we consider K1, M1 is the minimal, or here we can say minimum, possible non-zero value of this. So let's consider minimal of, because K is 1, it will be A1 plus A2 over 2 minus K is 1, A1 over 1. If we consider absolute value of this, it will be, if we use common denominator 2, A1 minus 2A1, we can write A1 plus A2 minus 2A1. Okay, you can say, okay, it is A2 minus A1 over 2. It should be minimum. The minimum of this is what? A2, it says non-zero, and A1, A2 are integers, the problem says. So, if we consider the minimum of this, it is 1 over 2. Because it cannot be less than that. A2 minus A1 is at least 1. Absolute value of that over 2, 1 over 2, if it is not 0, because it says non-zero. So, I consider is 1 over 2, but we should see, can we reach this case or not? If I consider K2 for M2, it's the last condition because N is 3. If I replace K with 2 here, A1 plus A2 plus A3 over 3 minus A1 plus A2 over 2 equal to, if we use common denominator 6, and 2A1 plus 2A2 plus 2A3 and on. At the end of this problem, I will leave some homeworks that you can solve again by small examples from IMO, from BMO round 2, BMO round 1 of other years. Okay, let's write the rest. Minus 3A1 minus 3A2. It will be what? It will be 2A1, 2A3, let's consider first. And 2A1 minus 3A1 is minus A1. 2A2 minus 3A2 is minus A2. All over 6. Again, because we want to find minimum non-zero element, numerator is at least 1. So it is, if we reach 1 over 6, it's the best case. So now let's see for N3, can we reach a good permutation? And if we can reach, it says find the number of ideal N-lists. So A2, absolute value of A2 minus A1 should be 1. And 2A3, absolute value of this numerator also should be 1. Because the minimum non-zero is this. 2A3 minus A2, because A1, A2, A3 are integers. And we know A1, A2, A3 are, they can be 1, 2, or 3. Okay, from 1 to 3. Now, let's just start from first one. A1. If A1 be 1, A2, because the difference is 1, A2 can be only 2. If we consider, so let's check this case first. A1 is 1, A2 is 2. A3, we know 2A3. From this part, let's consider this A2 minus A1 is plus or minus 1. So we can conclude A2 is A1 plus or minus 1. And from this case, 2A3 minus A1 minus A2, because absolute value is 1, so it is plus or minus 1. So 2A3 is A1. If you take negative A1, negative A2 to right side, it will be A1 plus A2 plus minus 1. So here, let's consider. And we can also say A3 is A1 plus A2 plus or minus 1 over 2. A1 plus A2 here is 3. 3 plus 1, 4 over 2 is 2. 3 minus 1, 2 over 2 is 1. So 1, 2, 1. Okay.
Now let's check if A1 is 2. If A1 is 2, A2 is A1 plus or minus 1. If it is plus 1, it is 3. If it is minus 1, let's check 2 minus 1, 1 first, and then 2 plus 1, 3. Now, I want to find A3. A3 is A1 plus A2, 2 plus 1, 3. 3 plus 1, 4 over 2 is 2, or let's write it again. 3 minus 1, 2, 2 over 2 is 1. Now, if it is 2, 3, 2 plus 3, 5, 5 plus 1, 6 over 2, 3, 5 minus 1, 4, 4 over 2 is 2. Last case, if it is 3. Then because A2 is this plus or minus 1, plus 1 is 4, it's not possible because n is 3 here. Minus 1, 2 is possible. 3 plus 2, 5. 5 plus 1, 6 over 2, 3. 3, 2. 5 minus 1, 4 over 2, 2. So we found 1, 2, 3, 4, 5, 6, 7, 8. The answer here is 8. We found 8 for N3. Now that we've learned these, let's do exactly same thing for general N. Okay, so let me copy the condition. Okay, let's go here. So for general N, the conditions are for K1. So for K1, again, we have A1 plus A2 over 2 minus A1. Let me correct this one. Okay, minus A1 over 1. It will be, again, like previous term, A2, if you simplify A2 minus 2A1 plus A1 minus A1 over 2 if you use common denominator. Again, we want to reach the case that A2 minus A1 in ideal case 1, and we want to see is it possible or not. If it is possible, again, like N3, how many cases? If case 2, and here we consider that A2 minus A1 again is plus minus 1, we've reached this. So A2 is A1 plus minus 1. In next case, A1 plus A2 plus A3 for K2, if we replace over 3 minus A1 plus A2 over 2. We've calculated this case before. We've calculated here. It will be exactly the same thing. I can copy this part because we've calculated. If you simplify, it will be this. And so the numerator should be 1 because the minimum non-zero. So 2A3 minus A1 minus A2 is 1. So we conclude that 2A3 minus A1 minus A2 is plus minus 1. And then we conclude that 2A3, if you take negative A1 and negative A2 to right side, A1 plus A2 plus minus 1. So A3, as we said, was A1 plus A2 plus minus 1 over 2. Now let's check, for example, for K3, and then we write for general K. For K3, it will be A1 plus A2 plus A3 plus A4 over 4 minus A1 plus A2 plus A3 over 3. If we use common denominator 12, look, you can say like previous terms. 3A4 we have, then 3A1 minus 4A1 minus A1. Again, 3A2 minus 4A2 is minus H. 3A3 minus 4A3 is minus A3. So here we conclude the numerator should be 1 for minimum case, 3A4 minus A1 minus A2 minus A3 should be 1. So because when absolute value of something is 1, then the thing inside absolute value is plus minus 1. Because the only thing that their absolute value is 1 are plus minus 1. Now, if we take negative A1, negative A2, negative A3 to right side, 3A4 is A1 plus A2 plus A3 plus minus 1. And then A4 equal to A1 plus A2 plus A3 plus minus 1 over 3. Now let's write for general case. For K, it will be A1 plus A2 to AK plus 1 over K plus 1 minus A1 plus A2 2ak all over k. Now, like previous cases, we can say, let's consider the common denominator be k times k plus 1. Again, k times ak plus 1, we write it because we have only here. Then for other cases, negative and k a1 minus k plus 1 a1 will be negative a1. K a2 minus k plus 1 a2, negative a2. Up to k ak minus k plus 1 ak, it's negative ak. Now here we conclude that the numerator should be 1, means because for the minimum case, k plus 1 minus a1 minus a2, the best case is that it should be 1, and then we want to see is it reachable or not. So when something, absolute value of something is 1, it is plus or minus 1. Again, we do the same thing, like small cases, minus a1, a2, minus ak, equal to plus minus 1. Then we take negative a1, negative a2 to negative ak to right hand side, so kak plus 1 equal to a1 plus a2 plus 2ak plus minus 1, and then we divide both sides by k. So we found a general formula for ak plus 1, which is a1 plus a2, 2ak plus minus 1 all over what? K. Now let's consider that, for example, for a1 we start with x, like previous case, like a small case that we said, okay, let's consider some a1 is 1, 2, 3 here, because ai's are from 1 to n, we say, okay, consider a1 is x. Now a2 we want to see can be what cases. A2 we've considered here, a2 is a1 plus minus 1, so it is x plus 1 or x minus 1. At first I write x minus 1 and here x plus 1. Now let's consider a3. The formula for a3 was what? Was this? Let me copy this part. Okay. Let's paste it here. In the first case, it is x minus 1, 2x minus 1 plus 1. So look, 2x minus 1 plus minus 1 over 2. 2x minus 1 plus 1 is 2x, and 2x minus 1 minus 1, 2x minus 2 over 2. So it will be x and x minus 1. X minus 1 we write first, and x. Okay. Now let's consider x plus 1. If you consider x plus 1, sum of them is what? 2x plus 1 plus minus 1 over 2. 2x plus 1 plus 1 is 2x plus 2. 2x plus 1 minus 1 is 2x over 2. It will be x plus 1 and x. So we write x and x plus 1. Now let's erase this part and let's focus on a4. By this formula, a4 when k is 3 is a1 plus a2 plus a3 plus minus 1 over 3. So let's check a4. For first case, x, 3x minus 2. 3x minus 2 plus minus 1 over 3. Because it should be integer, we should select minus and it will be 3x minus 3 over 3, which is x minus 1. The next one, x minus 1 x, it will be 3x minus 1 plus minus 1 over 3. So because it should be multiple of 3, a4 is that, we should select plus to be multiple of 3, because if you select minus, it will be 3x minus 2, which is not multiple of 3, and then a4 is not integer, but the problem says it should be integer. 3x over 3 is x. Third case, x plus 1 x, 3x plus 1 plus minus 1 over 3. We should select minus 1 here to be multiple of 3, 3x over 3, which will be x. The last one, 3x plus 2, x plus x plus 1 plus x plus 1, 3x plus 2, plus minus 1 over 3. Here we should select plus 1 to be multiple of 3, 3x plus 3 over 3, which is x plus 1. Okay. Now, something happened here. Up to A3, we had some cases, for example, x minus 1 or x, but in A4 it was unique, only x minus 1. It seems that all of them from here should be equal. We can check also A5. Let's check quickly by this way. It will be sum of previous ones plus minus 1. A5 is sum of previous one, A1, A2, A3, A4, plus minus 1 all over 5. Sum of previous one is 4x minus 3, over 4, because k is 4. 4x, sum of them, 4x minus 3. We should subtract 1 to be multiple of 4. 4x minus 4 over 4x minus 1. Here, 4x minus 1, you should add 1. 4x over 4x, again x. Here, 4x plus 1 minus 1x. And here, you can see that, okay, 4x plus 3 should add plus 1. 4x plus 4, it's x plus 1. Okay, now we want to prove that for each case, for the first case, all of them x minus 1 after a3, next one x, this one x plus 1. Let's prove it. Suppose up to ai we proved that it is, for example, for ai minus 1. We proved, or let's write ai. It's x minus 1, x minus 1. It is somehow like induction. If you want to write, for example, professional proof, you should say by induction. For I, for example, 1 to 5 or 1 to 3, 4, we've checked. There are these. We want to prove the next one, ai plus 1, is also same value as ai. So ai plus 1. Now if you check ai plus 1, ai plus 1 by this formula is a1 plus to ai previous terms plus minus 1 over what over I. Now, if we add this term for first case, we have ix. How many negative ones are there? Negative I minus 1 plus minus 1 divided by I. So here you should add, you should subtract 1. Let's see, it will be ix minus I plus 1 plus minus 1 over I. This part is multiple of I, so 1 minus 1. We should select minus 1. So if you select minus 1, this one will be cancelled. Ix minus I over I is x minus 1. Okay. Now let's consider second case. For second case, it will be ix minus 1, because we have only 1 minus 1, plus minus 1 over I. We should select plus 1 to be cancelled to be multiple of I. So it will be ix over this x. This one also is x. We proved. Third case. Sum of all terms will be ix. We have 1 more plus 1 plus minus 1 over I. We should select minus to cancel. So ix over I is x. Now let's consider last term. It will be ix plus this one, I minus 1 plus minus 1 over I. So if select minus 1, if select plus 1, they will be cancelled. Ix plus I over I is x plus 1. So we proved for general I plus 1 that it is same as ai. Now we can say, okay, up to an, the first one is x minus 1, then x plus 1. Now we know that the problem in problem ai is from 1 to n. So let's consider for first case, x should be what? X should be from 1. 1 is not possible because we have x minus 1 from 2 to n. It's possible. From this one, x has to be from 2 to n again. For third case, because we have x plus 1, it should be at least from x to n from 1 to n minus 1. For this case again, x has to be from 1 to n minus 1. Now, for each one, x can have n minus 1 cases. 2 to n, n minus 1, 2 to n, n minus 1, 1 to n minus 1, n minus 1, 1 to n minus 1, n minus 1. So each of them has n minus 1 cases. So the answer is 4 times n minus 1, and we proved. So let's check our small example. N was 3 here, and we had 4 times n minus 1. 4 times n minus 1 here, because n is 3, is 4 times 3 minus 1. It works. Okay, so we proved completely this problem. Let me write some homework that you can solve those homeworks with the same idea. They are from IMO, from also USAMO. One of them is for USAMO 2023, question number, let me tell you, 4, and USAJMO, it's for juniors, Q5. The problem, let me copy, as homework number 1, try to solve this one. I also released the video of this. You can solve again this one by small example. It is last USAMO problem, last years of USAMO. The homework number 2, again for considering small example. If you've not seen the solution of this problem, second problem of this exam, same idea, 2023. And next problem as homework number 3, it is for BMO1 2022, last BMO1 2022. I also released a video, the solution of this problem. You can find it in my channel. Again, I solved this with considering a small example. And also this problem, fourth problem of IMO 2020 as homework number 4. Again, you can solve this problem also with considering a small example. Okay, like considering a small example, we have some 3 ideas in paths and some ideas in double counting. They are useful in AMC, AME, USAMO, IMO, BMO, in all exams because they are background ideas. In combinatorics, we have in function problems, algebra, we have for example, considering special cases in function, checking that it's one-to-one or not, special cases, and some ideas to get rid of complicated terms. In combinatorics, we have algebra, geometry, and number theory. Geometry, we have 40, 50 important formulas you should memorize. They are useful in all exams. If you want to learn them, as I said before, and if you want to learn approaches, feel free to send message to my WhatsApp number in the description and comments. Okay. Okay, let's solve the last problem, problem number 4 of BMO Round 2 2023 British Mathematical Olympiad. The idea that we want to use this, at first pause the video and try by yourself, but the idea I want to use for this problem is same as the idea that is useful for IMO 20. In many problems it's useful. And let me tell you, after this problem solved, IMO 2020 first problem. Let me paste it here. Okay, so this problem, you can do it as homework. Take a screenshot from this problem and do it after this problem. So let's read this one. It says the side lengths ABC of a triangle ABC are positive integers such that the highest common factor of A, B, and C is 1. So let's write our assumptions. A, B, C are positive integers and highest common factor of ABC is 1, and angle A equal to 3 times angle B. Prove that at least one of ABC is a cube. Okay. So here, if you want to solve, one way is to, for example, say, maybe, for example, some of you want to work with this cos A because it is equal to cos 3B. We have a formula, but what we don't want to solve it this way, I just want to tell you. Maybe in some problems useful. It is 4 cos cubed B minus 3 cos A. Okay. And then, for example, we can replace cos A with cosine law equal to b squared plus c squared minus a squared over 2bc. But here, because we have the power of 3, then it will be complicated to work with. Now I want to tell you another idea that is also useful in IMO 2020 first problem. When you have, for example, angle A is 3b, you can divide the b to 3 parts, b, b, b. Also in IMO problem, you should use this. It works also for length. Sometimes, for example, you have angle A is twice, side A is twice side B. So you divide A to 2 parts, each of them B. Or A3B, you divide to 3 equal parts. So this idea is so much useful also in IMO and also other exams. So let's use this idea. Let me draw the triangle. Okay, in this part, it is A it is B, it is C, A is 3 times B. So I draw two parts, that's two lines to divide the angle A to three equal sides. This one 250, 280. Let me check. 250 because here the thing I've drawn it's 40, so it's 220, 260. Okay, 260 plus 40, 300. Okay, and the next one is 340. Yes, that works. Okay, it is angle B, it is angle B, it is angle B, it is angle B. Now, this angle, it is exterior angle, is B plus B, 2B. And this angle is B plus 2B, 3B. Okay. Now let's see which side, for example, it is, we call this one, let's consider this K, it is L. Because it is B, it is B, ABK is isosceles triangle, this one equal this one, because it is, let's see, it is 2B, it is 2B. So these two sides are equal, and we know it is B. So this one should be also B because the whole part is A, it is B, it is A, so this part is A minus B. Okay, so let me write A minus B, and let's consider, can we find any other length? Because it is A minus B, it is isosceles, it is also A minus B. Okay, up to this part, we've only used, for example, angle chasing, finding isosceles triangle. Now I want to tell you the theorems, the things we need. First, we prove them completely. As I said before, there are 40, 50 important formulas in geometry. Here we want to use some of them. Angle bisector theorem and general form of that and extension of that. Bisectors theorem. Then we generalize that, we use an application of that. The next one, Schwarz theorem, I want to use to solve this problem. And I will tell you both of them, and we will prove them, and then we will solve that problem. So let's focus on these two things first and prove them in a new space. Then we come back and solve this problem. So let's cut it and let's prove it here. So at first, let's consider angle bisector theorem. It is what? If we have a triangle, for example, ABC, okay, and we draw angle bisector like this one, internal angle bisector, and it is A, it is B, it is C, it is D, then we call it B, we call it C. BD over CD, it's famous theorem, equal to C over B. And it has lots of proof. Let me tell you one proof. For proving this part, you can say, for example, it is A over 2, it is A over 2. One way is to say that if we draw altitudes here, here, and we want to relate it to areas. Proof 1 and 2 related to areas. Proof 3 is not related to that. It's not related to that. So proof number 1, you say, okay, it is, for example, this length is x, this is y. You say if you consider area of ABD over area of ACD. Because if you consider this height, let's call, for example, this AH. For first one, ABD, it is height AH times BC times base BD over 2. For ACD, it is AH times CD over 2. Okay. We divide 2, we divide AH, so it is BD over 6. And then let's move it here. It is also equal ABD, equal to this height x times C over 2 y times b over 2. X equal to area of ACD. X equal to y. What? Y. Let's consider this big X, big Y. We can say because it is a over 2, it is, let me tell you, hypotenuse. So this one is 90 minus a over 2. This one is 90 minus a over 2. So by two angles on side between, we can say triangle AXD is congruent to triangle ADY. So we can conclude the corresponding sides X and Y are equal. Okay. Now we can divide X. We can cancel X and Y 2. So it will be C over B. It was proof number 1. Let me tell you proof number 2. Let me copy this part. For proof number 2, I don't want to use height. We have a famous formula for finding area of a triangle. Okay, the formula is what? Area of ABC equal to half times BC sine A. Okay, it is important and memorize it. The proof is not hard. You can prove it by yourself. So if you consider area of ABC, ABD over area of ACD again. So with one way we said altitude from this word AH is same, so it will be BD over C. But if you use this formula for ABD, it is half times C times AD times sine A over 2. And for ACD, it will be half times B times AD times sine A over 2. We can cancel sine A over 2, we can cancel AD, we can cancel 1/2, so it will be C over B. And let me tell you the last proof, because last proof can be also useful in some other problems. Last proof, I extend one side. Proof number 3. I extend, let me draw with other color. Extend, and I draw a line parallel to AD, okay? Something like this. This one. This. And we call, for example, this part E. It is parallel to this. This angle is what? Because it's A over 2, it is also A over 2. This angle is what? Because these two lines are parallel, it is also A over 2. And because it is B, it is also B. And we have a Thayer's theorem, we call it Thayer's theorem, and its application, or in some part you will see they say because of similar triangles. We know C over B, because they are parallel, equal to BD over DC. It is a famous theorem. C over B equal to BD over CD. It was the last one. Now, we've proved angle bisector theorem. Now the generalization of that is what? So let me copy our figure. I want to find BD and CD separately. Okay. And then I will apply it on the figure. BD, we've proved that by angle bisector theorem. BD over CD equal to C over B. Now, I say, okay, we write BD plus CD equal to, it's so much important in fractions that if you do anything on left hand side, you can do the corresponding thing to right hand side. You say, okay, numerator, you write here, you've written numerator and plus denominator. So we write numerator plus denominator, B plus C. Okay. And the proof is not hard. If you cross multiply, we have BDB like this. BDB equals CCD. Here, BDB plus BDC. Here we have also BDC. They will be cancelled and they are equivalent. But now we can find BD because BD plus CD is A. So BD is AC over B plus C. Because I've told you this, let me tell you some important thing in fractions. For example, when you have x, y, z, w, you can write, for example, x plus y, x minus y. You say, okay, it is z plus w. Here, numerator minus denominator. So you do the same thing, numerator minus denominator. Or for example, you can say x over y minus x equal, look, numerator over denominator minus numerator. You do the same thing. Numerator over denominator minus numerator. And the last part is if a1 over b1 equal a2 over b2 equal to ak over bk, we can prove the question mark that it is also equal to a2 to ak over b1, b2 to bk. The proof is not hard. Pause the video and try to prove first for yourself. The reason is you consider is t. So a1 is b1t, a2 if you cross multiply is b2t, and up to ak is bkt. So if you consider this fraction, I replace a1 with b1t, a2 with b2t, and ak with bkt. Denominator is b1 plus b2 to bk. So if you factor from t in the numerator, you can cancel b1 to bk. Okay, and it will be t again. So I proved this one for you. Now, here we proved bd. You should memorize it, and we want to use it in the problem. bd is ac over b plus c. And similarly, cd is ab over b plus c. If you do the same thing, here I say bd plus cd over cd equal to b plus c over b. And it will be, this one is a. So cd will be ab over b plus c, which is the thing I've written here. Now let's apply this in our problem. Here we can say, okay, this b and b, here we have what? We have angle bisector. AL is angle bisector. Let me copy this part that in this triangle, Control C, Control V, and the two formulas that we have, copy, paste here. Okay, let's use, look, BD is what? Is A, it lies on A times C nearest side over B plus C, okay? And here again, A, it lies on A times B nearest side over B plus C. So in this part, if I want to use, I say this part. I said this one is B, okay? The whole part case is B. So if I want to find this one, I said B times nearest side A minus B over A minus B plus B, like B plus C here. A minus B plus B is A. So it is this one, LC. Again, we know it is B. We proved in the beginning of the solution because we said this is equal to this because it is 2B, it is 2B, isosceles triangle. Again, we write B times this one, B squared over A minus B plus B, which is A. So we found these two lengths. Now in next step, I want to look in any problem of geometry. You should write the angles that you can. You should write the lengths that you can. It is important, for example, that we have angle bisectors, internal or external or median or perpendicular bisectors. So if you learn all formulas in medians and all angle chasing, all in angle bisectors, internal, external, all in perpendicular bisectors, all in altitudes, and learn cyclic quadrilateral in any problem. If you had internal angle bisector, you use, for example, like these formulas. If you have another thing, you can use, for example, altitudes, you can use them. So it's so much important to memorize the 40, 50 important formulas that we have in geometry. Okay. And for the rest of the solution, we need to know Stuart's theorem. Let me tell you the theorem is what and the proof is what. So if you have a triangle, it's so much useful because it is for an arbitrary line. So you can use the Stuart's theorem to find median, to find length of internal angle bisector, external angle bisector, and also other lines. It says if we have ABC, and if you have P, if it is X, it is Y, it is B, it is C, then, for example, this length, we call this one D. AP is an arbitrary line through A. The formula is this: xb squared plus yc squared log x times square of this side plus y times square root of c, square of c squared equal to a here times xy open bracket xy plus d squared close bracket. Let's prove it. The proof is not hard. If you memorize the idea is what, then you can easily always prove it. P1, P2. I use cosine law by cosine P1 in triangle ABP. If we apply cosine law, we can say cosine P1 is x squared plus d squared minus c squared over 2xt. If we use cosine law in triangle APC, cosine P2 equal to d squared plus y squared minus b squared all over 2yd. Okay. And because P1 plus P2 is 180, so sine of them are equal, but cosine, what's the relationship between cosine of them? Cosine P1 equal to negative cosine P2. If sum of two angles equal 180, sine of them equal, cosine of them are negative of each other. Now, if we combine these three things, cosine P1 is what? X squared plus d squared minus c squared over 2xt equal to negative of cosine P2. Negative, we can apply negative in numerator. On numerator, it will be b squared minus c squared minus y squared over 2yd. And then, okay, now we can multiply both sides by 2. We can cancel this. Multiply both sides by d. We can cancel this. And then let's multiply, cross multiply. Or we can say multiply by xy. So y times this, it's yx squared plus yd squared minus yc squared equal to xb squared, if we cross multiply here, minus xd squared minus xy squared. Now I take this one to right hand side, these two negatives to left hand side. So we have yx squared, let me write with other color. Here we have yx squared, we use this negative xy squared, if you take to left hand side it will be plus xy squared. And then yd squared plus yd squared. This one, if you take it to left hand side, plus xd squared equal to xb squared here, we have on right hand side. If you take negative yc squared to right hand side, it will be yc squared. Now, here in these two terms, if you factor from xy, it will be x plus y. And in these two parts, if you factor from d squared, it will be x plus y. And here it will be xb squared plus yc squared. X plus y is bc, is a. So as you can see, we proved this because axy plus axy plus ad squared equal to xb squared plus yc squared. So we proved Stuart's theorem. Now let's apply this. Let me at first erase this part. I want to copy and paste Stuart's theorem and apply that here. So let's copy. Okay. Let's move it to left. Now I want to use, let's see, it's good to use the Strauss theorem. Because I know AK, and here we call it C, I want to use in triangle ABC for line AK, I want to use the Strauss theorem. So A minus B times B squared times B squared plus, look at this XB squared. This one times C squared. This line was what? Was B, because it was B, it is 2B, 2B, B. Also, if you add these two things, it will be BA minus B squared plus this minus B squared will be cancelled. BA over A, which is B. So it will be B times C squared equal to A Here is a times x, y. So it is a minus b times this part, that is b, plus ak squared d squared, which is a minus b whole squared. Okay, now we can erase this part. Okay, let's erase this part. Now let's write this. Now we want to expand and simplify. Okay, so left hand side is ab squared. Let's write below that ab squared minus b cubed plus bc squared equal to a times ab minus b squared. This part is a squared minus 2ab plus b squared. B squared negative b squared will be cancelled. If you write, it will be a squared minus 2ab plus ab will be minus ab. Okay. Now in this part, let's see, do we have any important thing? And let's expand here a cubed minus a squared b. Now we will see all terms have b except this. So let's take this to left hand side. It will be ab squared here plus, let's write minus b cubed plus bc squared. These three terms, if you take negative a squared b to left hand side, it will be plus a squared b equal to a cubed. Okay. Now let's switch left hand side and right hand side. It's equal a cubed. Let me write it here. A cubed. Okay. Now I factor from b, it will be a minus ab minus b squared plus c squared plus a squared. Okay. Now I want to prove that b is a cube number. Let's see, can we prove it? If b is 1, the problem will be solved because 1 is a cube number. Otherwise, b is at least 2. So if I prove that the powers when a number is cube number, the power of each prime is multiple of 3. So suppose that p divides b and p is a prime. Okay. So because p divides b, p divides the right hand side. Okay. Because right hand side has b. So p divides also left hand side. Okay. Left hand side is what, a cubed. And because p is prime, p divides a. Okay. Because p is prime. Because if p is prime, p divides xy, you can say p divides x or p divides y. And because we have a cubed, p divides a or a or a, so p divides a. Now, p divides a, p divides b. We want to see that the problem says HCF of ABC is what? The problem says HCF highest common factor or GCD is 1. Here, highest common factor of ABC is 1. It means that because P divides B and P divides A, so P doesn't divide C. Now, if we analyze this, we know P divides this term, AB, because P divides both A and B, P divides B squared, P divides A squared, P doesn't divide C squared. P doesn't divide this. So if all of them are multiple of p plus c squared, so it is not multiple of p. P doesn't divide the whole term because you can also prove like this. You say if p divides ab, the bracket, plus minus b squared plus c squared plus a squared, we know p divides ab minus b squared plus a squared because p divides a and b. And if we subtract, then p divides c squared, and because p is prime, p divides c, so contradiction. So we proved that p doesn't divide this part. Now let's write again this equation. Control C. Okay, so let me open a new page. Okay. Now, this part, we know a cubed is this. We said if p divides b, we proved that p doesn't divide this. Okay, this for example, this part. So if we consider power of p in b, Because in left hand side power of p is multiple of 3, so multiple power of p in b also should be multiple of 3. Why? Because suppose a is, for example, p to the alpha times something k, which p doesn't divide k. The power of p is alpha here. So it will be p to the alpha k cubed equal to b also, suppose, for example, is p to the t times something times, for example, w, which p doesn't divide w. So in b, it will be ptw times ab minus b squared plus c squared plus a squared. Here, you know that p doesn't divide this. So left hand side is what? Let me move it here. If you raise to the power of 3, left hand side will be p to the 3 alpha times k cubed. So we know powers of p should be equal on both sides. So left side is 3 alpha, right side is pt. So power of p in b should be multiple of 3. You can say it for all primes that divide b. So all powers are multiple of 3. So b, the problem said what? Prove that at least one of b and c is a cube. So b is a cube. We've proved this problem completely. Okay. In number theory, working with prime numbers so much important. And for example, let me tell you some point. If AB is perfect square and A and B are relatively prime, you can say each of them should be perfect square. The next important thing is if AB equal to P times X squared, which P is prime, and again, if HCF or GCD of AB is 1, it is so much useful idea also in BMO previous years. A is, for example, PY1 squared, BY2 squared, or A, for example, is Z1 squared, and B is PZ2 squared. Okay, these two things. So try to, and let me write a homework for you that, because this problem was combination of number theory and geometry, let me copy a problem as homework. You can solve it with using number theory, working with primes, other things, working on HCF like this problem that HCF was 1. Do this BMO round 2 problem as homework number 1. And the idea I've told you here is so much useful. At homework number 2, try to solve IMO problem that the idea I told you in the beginning of the solution of problem number 4, that same as this problem. This IMO problem, try to do it as homework number 2. Okay. If you want to learn important ideas, basic ideas, and important like this, that is 3B. And for example, number theory, like this one that was useful, working on primes, working on HCF, that's also useful here. If you want to learn how to approach a problem, start from what point. For example, we've solved 2 problems here by the approach of considering a small example. There are also some other approaches in recursive sequence. An important question in recursive sequence you should ask, and you can solve IMO problem and represents what, but how to apply this question. And we can solve hard problem. In geometry also, we have some important ideas, as I said, in medians. Our lines are what? Medians, let me write. Medians, angle bisectors, perpendicular bisectors, and last line, for example, in this problem of BMO, angle bisector was useful, the rules in that, and some basic theorem like Stuart's theorem, Carnot's theorem, and also those theorems, each of them, for example, Siwa's theorem, we should consider them, but the most important thing are these 4 lines, altitudes. And then also we should work on cyclic quadrilaterals, so much useful in IMO problems and also in BMO problems. Cyclic quadrilaterals. If you want to know, and in each problem we have some of them, and you can use the ideas that we have here. If you want to know the 40, 50 important in formulas in geometry, and also the important ideas in combinatorics, number theory, and algebra functions. If you want to learn them, as I said before, feel free to send message to my WhatsApp number in the description and comments. And please don't forget to subscribe, turn on the bell, and like the video. Thanks. Bye.